CO2 molecules per kilogram solvent, the Henry coefficient would have had a very different use. So why did we do this? Well, first of all, it's interesting to see how a Henry coefficient is derived, how this solubility comes along. But it has also a very important practical advantage. Suppose we have the following case. We have measured the equilibrium adsorption constant, kappa, at a pressure of 5 atmosphere. But of course we are being asked to make a design of our carbon capture process at 2 atmosphere. So what do we need to do? Do we need to redo our experiment and remeasure our equilibrium constant at 2 atmosphere, or can we use our derived theory to make an estimate of the equilibrium constant at 2 atmosphere? Well, what we have derived is that at 5 atmosphere, the equilibrium constant is related to the Henry coefficient over the pressure. So we can calculate this Henry coefficient, and this Henry coefficient also holds at 2 atmosphere. And that is something we can now use to estimate the equilibrium constant at 2 atmosphere. From this calculation we get our Henry coefficient in terms of the equilibrium constant at 5 atmosphere, and we see that our kappa is a factor of 2.5 higher than the kappa at 5 atmosphere. So in this way we actually have used our theory to make a prediction of what would be the equilibrium constant at the different conditions than where we have measured it, and that is an example of the power of thermodynamics. What we can also do is we can do a similar thing if we would have measured our equilibrium constant at a different temperature. Well, that one is a little bit more complicated, and we will do that in a separate video. In summary, we have formulated the problem of knowing the equilibrium concentration of CO2 in our adsorber as an equilibrium process between CO2 partitioning between the vapor and the liquid phase. We have expressed this in a powerful thermodynamic equation, which only requires us to know one number, and that is the Henry coefficient that characterizes our solvent.
Okay, that's the last we're going to see of Professor Smid. Fine young man that he is. 90 seconds for you to work with your friends, okay? An epiphany, an extension, or a question. Epiphany, extension, or question.
Okay, time's up. February birthdays. February. There's a surprising absence of birthdays. March birthdays. March. How about a volunteer?
Yes, sir, and the checks.
It's a big question.
The thing is that, sir, point is that we are talking about an equilibrium for carbon dioxide in the liquid phase and the gas phase. But the thing is that that would highly depend upon the kind of solvent we are using and the properties of solvent. If solvent we are using water, then it should be pure. Otherwise, if it's not pure, it has some impurities that would reduce the efficiency of the system. And if you have to get that pure water, what is the cost of that producing that pure water? That would also enhance the cost, cost issue also. And secondly, sir, the overall, efficiency problem. What would the efficiency of the system if we use impure water or if we use pure water? That would, pure solvent, impure solvent. That would also make a big time difference to them.
Yeah, those are nice comments. Thank you very much. Indeed, the chemistry of the solvent is a really interesting design tool. So those of you who are chemists, you might ask, how could I craft a molecule that would be perfectly
trying to take CO2 from this mixture and yet not take it so strongly that it couldn't be easily regenerated. And this is the research strategy of many of our colleagues in the chemistry community. And indeed, they have to do the calculations of the Henry coefficient for all those solvents or measure them. Some people can use quantum computational methods and statistical mechanics methods. But in many cases, you just measure them. And it is true, the Henry coefficient depends on what's in the water. And so one of the things we want to do is understand in more detail the role of impurities on the Henry coefficient. The good news is that for water, dilute impurities make little difference. But when you talk 10, 20, 30, 40%, then things start to matter. So, but solvent design is an upcoming video. Okay, so. Another question, I saw somebody else's hand, didn't I, a minute ago? Sorry. Somebody else have a question?
Because carbon dioxide, along with carbon dioxide, there are a number of gases.
Yeah, so let me just say broadly that there's an analytical chemistry problem when looking at the equilibrium
Of a gas between two thermodynamic phases. How do you measure what's there? The good news is that CO2 is very, very easy to detect because it has a very characteristic vibration. So a little infrared spectrophotometer can tell you CO2 in the liquid and gas phases. What's that? Infrared spectrophotometer, right? Yeah, infrared. Okay, I think we have time for one more, but I want to just, you may have missed what I think is the most important point from Professor Smith, which is you have this XY diagram. There's a line on that diagram that represents the conditions of thermodynamic equilibrium. So now Professor Wendt will come on for a few moments and tell us about conservation of mass. Are we okay? Are we okay with one more video? Yeah, all is good? Yeah, okay. Here we go.
Hi, welcome to the Berkeley Lectures on Energy. I'm Marjorie Wendt, and in this video we will look at mass transfer analysis in an absorption column. We're going to see how the principle of conservation of mass, along with equilibrium data, allow us to mathematically analyze these systems, and also how graphical analysis can be used as a design tool. So let's start with a review of the absorption process as patented by Robert Bottoms in 1931. We have two units, the absorber and the stripper, and we have flue gas coming in from a coal-fired power plant containing carbon dioxide. As it rises up the absorber, the solvent absorbs carbon dioxide, and we have mostly pure nitrogen coming out at the top. Over here in the stripper, steam is added to heat up the solvent and desorb the CO2, which comes out as mostly pure CO2. What we want to know in these systems is how much solvent will we need, how much energy will this require, how big does the thing need to be to handle all the carbon dioxide coming from the plant. When you do the calculations, what you will find is that the amount of solvent required is enormous. So let's review what's happening on one plate in the absorption column. We have liquid and vapor, and what we want to do is get the carbon dioxide out of the flue gas and into the liquid solvent. Ideally, we would achieve equilibrium on each plate in this column. And we can represent that graphically, where we are using Y to denote the vapor phase mole fraction and X to denote the liquid phase mole fraction. We know empirically a straight line, and we use a coefficient K, the Henry coefficient, to describe the slope of that And we also note that lines for different solvents have different slopes. So this dimensionless Henry coefficient describes the vapor-liquid equilibrium for a solute in a particular solvent, and it depends on temperature. Now for CO2 and water at 25 degrees C, the Henry coefficient is 1600. That means the slope of this line is 1600. This equilibrium line will form the starting point for graphical analysis. So now let's look at how we can invoke the conservation of mass to derive equations which will serve as design tools for our system. Let's start with a mathematical description of our absorption column with the variables labeled as shown. So we have 6 variables. 2 are the molar flow rates of the solvent and of the flue gas. 2 are the gas phase compositions, that entering in the flue gas and that leaving in the exhaust. And 2 are the liquid phase compositions, that entering in the regenerated solvent in the stripper and leaving in the saturated solvent. So of those variables, some are constrained, this being a downstream unit. The molar flow rate as well as the composition of the flue gas are determined by what's happening back in the combustion unit. Now the regenerated solvent mole fraction is determined by what's happening in the stripper, and ideally that will be a number that's very small, close to 0. The mole fraction in the saturated solvent will tell us about how much CO2 that particular solvent can hold, and ideally that will be in equilibrium with the CO2 in the flue gas. So what's our design goal? Our design goal is going to be this vapor phase mole fraction in the exhaust. That's basically how much CO2 we're willing to tolerate leaving this system. So for example, we could say we want to capture 90% of the CO2 that comes in flue gas. So that leaves us for an operating variable, the flow rate of the solvent. That's what we're going to be adjusting to try to reach our design goal. And the equations that we have to work with are the equilibrium relationship, Henry's law, which we've just seen, as well as the conservation of mass of carbon dioxide. So the mass of carbon dioxide must be conserved over the entire absorption column. So we can write a mass balance that looks like this: input minus output, plus generation minus consumption equals 0. And assuming no chemical reaction will generate or consume dioxide, we have moles of CO2 going in as moles of CO2 going out. So we simply multiply the molar flow rates by the compositions, and we have going in the liquid phase and in the gas phase equal to the moles coming out in the liquid phase and in the gas phase. We can rearrange this equation and solve for our design goal here, the vapor phase mole fraction in the exhaust, and we see that as a function of the other variables. So we can plot this point on our XY graph, and here we have the gas phase composition in the exhaust, and we can plot that against the liquid phase composition in the regenerated solvent, and this point represents the top of the absorber. So the overall mass balance has given us a point that represents the top of the absorption column. We add that to the equilibrium line, and we have the starting point for the graphical analysis. Now we're going to apply a mass balance over a control volume, which we can draw around the top of the column and an arbitrary plate P+1. So this column contains a series of plates, and we'll number them starting with number 1 at the bottom and going up as we go up the column. So now within this control volume, we can write our mass balance for CO2 as we did before and equate the moles going in to the moles going out. In this case now, the moles going in the vapor phase are what's rising up plate P below, and the moles exiting in the liquid phase are what's falling from plate P+1 down to plate P below. So again, we can write the equation and solve for Y. In this case, we're solving for the vapor phase mole fraction on plate P as a function of the liquid phase mole fraction on plate P+1. And this looks like an equation for a line in the form Y equals mx plus b, where the intercept here is the exhaust composition, and the slope is going to be this ratio of the solvent flow rate to the flue gas flow rate. So we have another point to add to our graph here, and this came from the mass balance, and expresses that all of the carbon dioxide that enters at the top of the column or at plate P must leave at the top of the column or at plate P. So this relates the vapor phase mole fraction on plate P to the liquid phase mole fraction on plate P+1. So let's put this all together in one graph. We started with the equilibrium line, which expresses equilibrium between the vapor phase and the liquid phase on any plate. We add the top of the absorber, and now we're going to add this operating line, which expresses the conservation of mass in a system containing the top of the absorber and any plate P. So this relates the mole fraction of the vapor phase on plate P to that of the liquid phase on plate P plus 1. These mass balance equations, or operating lines, form a family of lines with slope equal to the ratio of the solvent flow rate to the flue gas flow rate. As that slope increases, the lines move away from the equilibrium line. So now we can look at one plate P on our graphical analysis. So from the liquid phase composition on that plate P, we can use the mass balance, or the operating line, to get the composition of the vapor that came up to that plate from the plate below. And we can use the equilibrium line to get the composition of the vapor on that plate that is rising to the next plate above. So in this way, each plate on the absorption column is represented by this triangular space in between the operating line and the equilibrium line. So this concept of representing plates on our graph forms the basis of what's known as a McCabe-Thiele diagram. You can learn more about that in further videos. But the basic idea is that we start with our flue gas concentration here, and we simply march down and mark off stages or plates in the column until we get to our design goal, the gas phase composition in the exhaust. Now let's make a little comparison here of two scenarios where we've changed the slope of the operating line, or the liquid to volume flow rate. So over here with a steeper slope, we see that fewer stages will be required, whereas over here with a slope that's less steep, we see more stages will be required, but we'll be operating closer to equilibrium. So something for you to think about is which of these has a higher capital cost, and which will have a higher energy cost. So let's review the assumptions that we made to get to this point in our analysis. We assumed low solute concentrations, so Henry's law regime. We assumed that the molar flow rates of both the solvent and the flue gas remain constant, so no evaporation or other losses of solvent and relatively small amounts of carbon dioxide being transferred. And we assumed that only carbon dioxide transfers between the two phases. So in conclusion, we've seen that the mass of the solute is conserved at each stage in an absorption column and in the entire absorption column, and that graphical analysis based on the conservation of mass, together with equilibrium data, can be used as design tools for absorption systems. And this analysis will allow us to direct research, ultimately to improve the design, and an improved design is going to mean less solvent, less energy, and less cost.
I want you to take 1 minute with your neighbor and answer the question in green at the bottom. And you're looking at those two diagrams up there, okay? 90 seconds. No, 1 minute, 60 seconds.
Okay. So we have two designs, one of which has 2 plates to go from here to here, and one of which has 5 plates to go from here to here. Which one has the higher capital cost?
Two-step process? The one which has two-step process?
The higher capital cost.
Higher cost.
Sir, 5 with the 5 units.
How many people say 5? Raise your hand. How many people say 2? Raise your hand. It's okay. So if you think about, remember the first video in which Professor Smith showed these plates that have holes in them, and they're going to be distributed in a tower, and you saw pictures, some of those towers are many stories high. So in general, we assume more plates is more cost, because each one of these plates is stainless steel or some sort of crafted device. So we would guess that the capital cost is higher for this one than this one. I'll leave it for you to discuss amongst your friends what the higher energy cost is. It's not so obvious in a particular case. And the reason we're spending so much time on absorption is because of all 3 technologies that are possibly deployed for CCS. This is the most mature. It is ready to go. You can call up a company today and they will deliver a device that will do this absorption process for you. So that's why we're spending a little more time on this. Also, Professor Singh told me that I speak too fast. So maybe having these videos will slow down a bit. So on Thursday, tomorrow, at 2 o'clock, we'll start with the last 2 videos. They're actually me talking this time. And
and we'll talk about rates and talk about solvent design, and then we'll switch and talk about adsorption. Okay, so that's where we're going tomorrow. I'll see you then.